Hi, my name is Agt Hv. In this video, we will describe the design of the high voltage homopolar generator. The generator is you apply a magnetic field and you apply a force and you get current, electrical energy. It converts mechanical energy directly to electrical energy. This is the logo for the high voltage homopolar generator. I'll explain the meaning of the logo at the end of this video. So basically you have for the generator, the one we're going to use is the cylinder method, where the current is straight and the B field is radial, and so the high voltage homopolar generator video series comprises of three sections. The first is the first design attempt, which does not work, and then we'll do the slot analysis, understanding why the first design does not work, and then we'll do the final design which works. The high voltage homopolar generator first design attempt. The first design attempt was based on shielding the return path of the induction coil loop. The design is described. The basic design principles for the high voltage homopolar generator are introduced, and they're also applied to the final design and will not be repeated in the discussion of the final design. Voltage is equivalent to magnetization force, which is in ampere terms, and we can either use an electromagnetic coil or a permanent magnet. So basically this is the circuit where you have a voltage. In this case you see a current come down the middle, which is through the cylinder surface, comes out the sides and back up and completes the circuit. So what we want to do is, throughout the path, you want to keep the B constant, always at 1 Tesla, especially in the area where it's cutting the field. Also, we can put two electromagnets or two permanent magnets, and this is the method that was chosen for the first homopolar design attempt. So we use two electromagnets and we go through the sides and back up and through the center. This is the design that we chose for the final design, which is a single coil in the middle, and we have the magnetic field, the flux density go up, and once on the left hand side and down on the right hand side. The formula for both the generator and the motor thrust are a function of B, the magnetic flux density, or the B field. For generator, voltage equals the rotational speed times the radius times the length times the B field, and for the motor thruster is force equals the current times the length times the B field. I'll explain these formulas later, but I just want you to realize that these two formulas depend on B. You start your designing by determining at what B level you want to operate at, usually at B equals 1 Tesla. And then you determine the number of turns for the B field coil to produce this B field. If there are air gaps in the magnetic path for this coil, the core effect is ignored, and you can approximate by just calculating the ampere turns for the air gap length to give 1 Tesla. At B equals 1 Tesla, for air it is 800 ampere turns per millimeter. For 1008 steel core it is 0.3 ampere turns per millimeter. That is why it's ignored as a first approximation. It's so small compared to 800. Example, if the air gap is 2 millimeters, then it requires 1600 ampere turns for the B field coil. It can be 160 turns at 10 amps per turn, or 1600 turns at 1 amp per turn. The cross-section area of the core has no role in determining the ampere turns of the coil. you'll need 16 ampere turns whether the cross-sectional area of the core is 0.1 meter squared or 1,000 meters squared. That is why for devices, example core radius 50 millimeters or less, it's practical to use a permanent magnet instead of an electromagnetic coil. For devices with core radius greater than 50 millimeters or 4 inches diameter, it is best to use an electromagnetic coils instead of a permanent magnet. The inner core cross-sectional area that you determine for the B field coil is determined by the amount of induction voltage induced on each turn and segment you want to have on the induction coil. The bigger the radius, the much bigger the induction voltage. Example, doubling the core radius in the formula V equals WRLB. Doubling the radius, it will double the length, double the number of turns you can place on the surface of the induction area, resulting in V increasing by 8 times. This cross-section area underneath the B field coil must be maintained fairly the same throughout the magnetic path length to avoid core saturation in case of a smaller cross-section area than the cross-section area underneath the B field coil, or wasted material in case of a cross-section area larger than core cross-section area underneath the B field. I'll use R instead of small r for radius. So circular area is pi RR. Vertical path area starting from the top of the circular inner core, you want to set the width to equals R. So here's an example. There's a slot in teeth here. This is the inner core. This from here up, this is the outer core. Just showing the ends where the magnetic field path comes through here and down through the inner core and back out like a loop. Do not try to build this type of device, it does not work. So the magnetic path will be basically, this is the outer core, the blue is the outer core, come down and around and back up. These are the B field coils, these two reds. So to summarize, the disk area on the two ends surface of the cylinder. Cylinder area is on the surface along the length of the cylinder parallel to the axis of the cylinder. Cylinder induction is the induction on the right surface. This V equals BWLR. Disk induction V equals BWRR for the two ends surface. So the two ends surface together, but if you're only using one disk surface, then it's half BWRR for a single end surface. V is the induced voltage per wire turn or segment. B is the magnetic flux density in Tesla. W is the rotational speed in RPM, revolutions per minute. L is length of cylinder in meters. R is the radius of cylinder in meters. So the voltage is VWLR. I normalized to 1.8 volts per turn or segment. That's with the following condition: B at 1 Tesla, W at 1800 RPM, L 100 millimeter, and R equals 100 millimeter. B is the same on the cylinder surface or on end disk surface when L equals R. End surface disk area is bar R. For two end surface combined is 2 pi RRR. Area along the length of the cylinder area is circumference times length, which is pi times 2R times L, where L is the length. If L equals R, then the cylinder area equals 2 pi RR equals 2 pi R, which proves that when L equals R, the cylinder surface equals the area of the two circles. Keep L equals R to keep the flux density be the same throughout the cylinder. Most of the reluctance will be in the air gap. If the air gap reluctance is more than 10 times greater than the rest of the total remaining reluctance, then use only the air gap reluctance as a good approximation. The ampere turns for air is 800. The air gap, that's for an air gap of 1 millimeter and the flux density at 1 Tesla. If the air gap length is 1 millimeter, the required ampere turn is 800 ampere turns. 800 coil turns at 1 amp or 400 coil turns at 2 amps. Most of the reluctance will be in air gap. So the output voltage is voltage per turn times the number of turns. Normalized V out is 1.8 volts times N for B 1000 RPM equals 1800. L equals R equals 0.1 meter or 100 millimeters. The output power is the output voltage times the output current. So voltage times I out. Power losses is I squared R. The total resistance of the coil times the current squared. In case of electromagnetic configuration, there is copper losses in the induction coil and copper losses in the B field coil. Induction coil losses, output current squared times induction coil resistance, I out, times R induction coil. Again, this is a basic motor or generator configuration. Here showing with two permanent magnets. When an electromagnet is used to replace the permanent magnet, it is called the B field coil. We can add multiple turns to the coil here, and then this becomes called the induction coil. Here shows the configuration for design. This is the width of the vertical magnetic path. This is the height of the teeth, and L is 100 millimeters, the radius is 100 millimeters, and the R from the center to the top of the teeth. That's where the conductance are in the air gap, and that radius is under 20. So effectively R is 120 millimeters. Inner core radius is R 100 millimeter. Inner core disc area equals pi R squared equals 31,400 millimeters square. This is the standard area for B equals 1 Tesla. At the start of the vertical magnetic mean path from the inner core, the area is the inner core circumference times the width. So equals 2 pi RW, and this area must equal to the inner core disc area, which is pi RR. So 2 pi R, so that gives you R equals R over 2. So the width has to be 50 millimeters to keep the surface area, the area is equal, so that you still keep the density, the B field at 1 Tesla. So we designed the tooth to slot height at 20 millimeters minus H. So we use 20 millimeters chosen. The radius of the bottom of the outer core is 100 millimeters plus 20 millimeters. So it's 120 millimeters. This is the induction area where the horizontal conductor segments are located. So the cylinder area is increased by 20%, and say the slots take 10% of the cylinder area. The B field doesn't flow through the slots, the larger air gaps, because they have a larger air gap. So we're still off by 10%. So we can just L by decreasing L by 10%, or we can increase the current on the B field coil by about 10% to give B equals 1.1 Tesla at the inner core and 1 Tesla at the cylinder surface. So that's where radius equals 120 millimeters. So we maintain L equals R. So this, the cylinder length where the cylinder area equals the two disc areas. Outer core area equals outer mean circumference times thickness. And this area must equal to the inner core disc area, which is pi R squared, which is the 31,400 millimeters squared. We can take a guess at the thickness, say T equals 40 millimeters and T over 2 equals 20 millimeters. So the outer core mean radius is 120 plus the thickness divided by 2, which is 140 millimeters. The outer mean circumference is 2 pi times 140 millimeters, which comes at about 900 millimeters. The outer core area is times the thickness, which is 35,000, and this is larger than the 21. We leave it as it is, or we can try lowering to say 36 millimeters. So we did a second trial. The outer core R mean is 120, right? So the area now came to 800. The circumference came now to 866.6, and the area came to 31,199 millimeters square. It is still slightly lower than the 31 for we'll leave it as it is, or we can try increase by 1 millimeter and recalculate, but that's close enough. Do not confuse coil magnetic path length to coil length. Magnetic path length is used for determining the number of turns for the coil. Coil length is the actual wire length of the coil, and it's used for determining the coil resistance and the power dissipation or consumption of the coil. In all three devices there are two types of coils, the B-field coil and the induction coil. The B-field coil is an electromagnet that is used instead of a permanent magnet to produce the B-field. The induction coil is where the voltage is induced due to the rotation of the induction coil in a B-field. So here's the steps. Determine the working flux density, usually B equals 1 Tesla. Use the BH curve to choose the B point on the linear portion of the curve as close as possible to the saturation point. Determine the air gap, e.g. 1 millimeter based on choice of the output coil wire size, or it can be 2 millimeters. Determine the ampere turns from the formula for B1 1 Tesla and air gap 1 millimeter. If the air gap is 1 millimeter, then it's 800 ampere turns. Determine the bobbin size, wire size, and number of turns. The B-field coil copper losses. Keep L equals R to keep the constant B throughout all surfaces. L may be slightly bigger than R to compensate for air loss due to the slots. Determine R or L based on V equals 1.8 volts per segment or turn. For R equals 100 millimeter, L equals 100 millimeter, B equals 1 Tesla, RPM 1800. That's what gives you 1.8 volts per segment. But if you change these values, you change by a factor. Based on the expected output power, which is in turn determined output voltage and current, the number of turns or segments, and the wire size on the output coil. Calculate L percentage increase to keep the B constant due to slot and percentage decrease due to slot height. Calculate the total output voltage. Determine the total output resistance of induction coil. Determine the current limit, load limit based on the induction coil. Determine the induction coil loss at maximum I load. Determine the induction coil power loss, I load squared times induction coil resistance. Here's an example. Here shows the magnetic path and the air gap, say 2 millimeters. At 1 Tesla, the required air gap ampere turn is 800. For 2 millimeter gap requires 1600 ampere turns. For the magnetic path in the core, it's here showing an example. The height here is 125 millimeters and the length is 100 millimeters. So it's 2 times that is about 450 millimeters or 0.45 meters. From the BH curve for the core at 1000 at B1 Tesla, from the curve requires 300 ampere turns per meter. Therefore, for a path length of 0.45 meters, it requires about half of that, which is about 150 ampere turns. Note that the cross-section area has nothing to do with determining the field coil ampere turns. Also note that for a good approximation, all that is needed is just to calculate the required ampere turns for the air gap. There is no need to calculate the core mean magnetic path and the ampere turns for the core if it is estimated to be much less than the ampere turns for the air gap. Now that you determine the ampere turns, approximately 2000 ampere turns, which most of it is for the air gap of 2 millimeters. Now is to calculate the size of the field coil. Choose 1 millimeter by 1 millimeter wire or 1 millimeter diameter wire, and if it's not constrained by space, choose the current through which the wire will be as minimum as possible to reduce the power losses. Power losses is I squared R. Choose 1 amp per turn, therefore the total number of turns required is 2000 turns. Choose a square that is going to fit the wire square area. Usually for a 50 millimeter by 50 millimeter, you can probably put 2500 millimeter square. You should be able to fit 2000 turns since each turn takes about 1 millimeter square. Say that the core inside the coil has a radius of 100 millimeters. the coil number of turns, mean radius is 100 plus 50 divided by 2, it's 125 millimeters. The length of one turn is the circumference using the mean radius, which is about, so the length of one turn is about 0.785 meters. The total length of the coil is the number of turns times the length of one turn, 2000 times 0.785, which is 1570 meters or 1.57 kilometers. The resistance of the coil is 1.750 kilometers times, because the resistance of 1 millimeter diameter is approximately 20 ohms per kilometer, so that gives you a total resistance of 31.4 ohms. So the power consumption is current squared times the R, which shows to be 1 amp, comes to 31.4 watts. Slot shielding. In this presentation is the only time I will introduce enhancement to the currently accepted theory about magnetism. It does not replace the existing accepted concept for magnetism, but it enhances in order to explain why in a shield or a slot with no flux in it, it still induces a voltage on the wire. Also for the homopolar induction condition, when rotating a disc magnet and a conductor stationary does not induce a voltage, or when rotating a disc magnet together with a conductor still induces a voltage. The entire design for all three devices uses currently accepted design equations. So a shield, in a good shield there is no flux inside the shield. All the flux goes through the core. A slot is also a good shield, and the B field is not present in the slot and flux cutting cannot occur. So the B field goes around the slot and there's no flux inside, there's no flux cutting occurs inside the slot. So the prior experiments, this is from a document, Electrical Engineering Industry and Science, volume XL, from October 29, 1897. And here the author did some experiments. He placed coils, which then he did without a shield and put a shield around it. And the coil is looped so that the current is flowing in the middle and out at the top, so that if induction occurs on both, then the net voltage is zero. Current flowing into the page on half of the coil and out of the page on the other half of the coil, the sum would be zero. After the coil is placed in the shield, the sum is zero, whether shielded or not, indicating induction still occurs in the shielded portion of the coil. So this is just an enlarged. So here's another paper. This is called the Resolution of the Faraday Box by Skolov, Kennedy, sorry for mixing up the names, Bevin, Walter, Shubakin, and Anatoly, Skolov, Vitaly, and Lloyd Depp, Valerie. And it says, while simultaneously rotating the disc and the magnet, the field does not rotate and an EMF is induced only in the disc. And he says, while what they did, they tried to put the wire going in, the return going through a shield. And it says, we discovered an effect that was not known to us. Screens that confidently protect the conductor from induced EMF with a very magnetic field do not work when the conductor moves relative to a uniform magnetic field. So basically the shield doesn't do anything. But this effect was known as far as back in 1897, which was the previous paper that I showed. It was known that induction still occurs on a moving shielding conductor. The big question is why? But before we go there, let's review some of the basic induction methods before answering the question. So there's two methods. There's flux cutting and flux leaking. Flux cutting is the conductor moves, flux density B remains constant. We use the right hand rule for determining the polarity of the voltage induced or the direction of the current. Thumb in the direction of motion, index finger in the direction of the B field, and the middle finger in the direction of the current. So flux linking is the conductor stays still, but B changes. So here's an example. B is increasing here, B is decreasing, is equivalent to B increasing in the opposite direction. Use the left-hand grip rule for determining the polarity of the voltage induced or direction of the current. Wrap your left hand around the B vector, which is this, and thumb points in the direction of B increasing. The fingers point in the direction of the current induced. Note, B decreasing equals B increasing in the opposite direction. So reviewing is, so on the left hand side you've got the B field decreasing, and on the right hand side we have the B field increasing. So they both induce the same polarity on a conductor. Applying the left hand grip rule on the decreasing magnetic B field on the left side of the conductor induces a voltage into the page. Applying the left hand grip rule on the increasing magnetic field vector on the right side of the conductor also induces a voltage into the page. So this is the same as this. So it's a B field decreasing is equivalent to B field increasing downwards, which is similar to a coil surrounding a conductor. Note that when the field and the currents are orthogonal, i.e. the field vectors and the current vectors are at 90 degrees to each other. So this is the graphical representation. Field vector parallel to the page. There's a field vector, voltage or current vector into the page. So this is like a coil too, where we have the B field increasing, induces a voltage. They're shown by the red current for the red arrow for the current. So this is where the modified or the enhancement to the magnetic field. The magnetic field does not move with a moving object. In a moving object, in a moving body with a magnetic field, the magnetic field on the lagging end of the edge is extinguished, and on the leading end, this is the lagging edge, if the motion is to the right. So the field here is being extinguished, here the field is being increased. In the middle of the magnetic field, the magnetic field does not move with the body and it is stationary. So the field in the middle, the black arrows, is not moving, it's stationary, it is constant. Field on this edge is decreasing, being extinguished. Field on this edge is increased, being created. These are the red arrows, they're the ones that are changing. The edge field decreasing and increasing induces a voltage by flux linkage. The middle stationary field induces a voltage by flux cutting. The induced voltage by flux cutting, which is by applying the right hand rule, and by flux linking, applying the left hand grip rule, are in the opposite polarity. With the conductor placed inside the field of the magnet and moving together with the magnet, the rate of flux cutting equals the rate of flux linking, and no net voltage is induced in the conductor. Here's an example of more in detail of a conductor moving with the magnet. The conductor together with the magnet moves across 3 field vectors to the right. The conductor cuts 3 stationary field vectors, and at the same time 3 field vectors were these 3, because this is the conductor, it moved 3, and these 3 field vectors here were extinguished, shown by the red dot. At the same time 3 field vectors were created on the right hand side, but these 3 field vectors remain stationary and do not change. But however, the conductor moved from here to there, which cut 3 stationary field vectors. No net voltage is induced because the rate of the field cutting equals the rate of field flux cutting and flux linkage are equal and opposite. Now let's look at the shield conductor moving to the right. So I label the vectors from 1 to 11. So you see vector number 2 is inside the shield, and 5, 6 is on the right hand side. So when we move across on this side of the shield, vector number 2, was the original position, went back to the outside. It was created on the outside, but at the same time it was decreased from inside of the thing. So these two cancel. On the left outside edge of the shield, flux number 2 is extinguished from the shield, but at the same time is created outside of the shield. Therefore, no net change in flux with respect to the inductor. The inductor here does this, the two cancel with respect to that. The same applies to the right outside edge of the shield for flux vector number 10. So number 10, it was on the outside, it decreased, it extinguished from here and got created inside the magnet. I mean inside the shield, so there's no net change. But however, inside the shield, there's no flux, and because there's no flux, number 6 vector at the shield conductor moves to the right. Number 6 field vector is extinguished from the right side edge of the cavity and induces volume broken up by flux linking. This is the same effect as if the clock was cutting the field. So number 6 is to be on the right hand side. It decreased, got extinguished, and it was created on the left hand side. So that induced a voltage on the conductor. Now let's go back and review the difference between a bar magnet and a disc. This is what we had before. A magnet stationary, and a conductor moving, voltage induced in the conductor. This is the same with the disc magnet stationary and a conductor moving. Voltage, both are the same. Now, magnet moving, conductor stationary, voltage induced on the conductor. Here, this magnet moving, rotating, conductor stationary, no voltage induced on the inductor. Magnet and conductor moving together, no voltage induced on the conductor. But here, this magnet and conductor moving together, rotating, voltage induced. So let's go back and review the difference between cases for induction. Then we apply the new rule that the magnetic field does not move with the object and check if it holds. Now, magnet stationary, conductor moving. Flux cutting only, voltage induced on the conductor. Right hand rule for flux cutting, left hand grip rule for flux linkage. Magnet moving, conductor stationary. The flux linkage from the edges only. So in this case, you got the flux decreasing here and flux being created here, and voltage induced on a conductor. Magnet and conductor moving together, flux cutting and flux linkage. No voltage induced on the conductor. Flux linkage from the edges cancel the flux cutting. The rate of flux cutting is the same as the rate of flux linkage. Now let's look at the disc magnet. Stationary. Conductor moving, rotating, voltage induced on the conductor. Now disc magnet moving, rotating. Conductor stationary. No flux linkage because no flux cutting. So no voltage induced because there's no edges, there's no cuts. This magnet and conductor moving together, rotating, flux cutting, no flux linkage, voltage induced on the conductor because the B field is stationary. So again, we use the flux cutting, you use the right hand rule. This is a refresher, reminder of how I apply. And for flux linkage, we use the left hand grip rule. This is how it's applied. No B field exists in the slot. No B field exists in the slot since it is a shield, but flux cutting on the two side is flux cutting here, and flux linking in the slot. The voltage induced is the same in magnitude and direction out of the page. So having a small slot and a tooth, they both induce a voltage in the same direction and the same magnitude. From the perspective of the inductor on the tooth, the field change on the edges of the slot, the pair cancels and has no effect. So from looking from here, it's rising, it's decreasing, they cancel each other, it has no effect on the conductor on the tooth. From now on, this is the representation of edge field change. Also, we represent the pair induces 1 unit in the conductor in the slot. The flux cutting is also induced 1 unit in the conductor on the tooth. The conductor in the slot behaves as if the conductor was on the tooth. Therefore, cannot be used as a current return path for the conductor on the tooth. So here's a case where we have one single conductor and no slots. So it's all flux cutting only. So it's like 100% tooth. So here's 2 other cases. The duty cycle, which is the ratio of the tooth width to the slot width, also has an effect. Case, the ratio of the tooth width to the slot width is about 9.1. Tooth large, slot small. So this is the case where we have a large tooth and a small slot. So here it will behave as if was the voltage induced here is almost 100% or 1 unit, and our voltage also there will be almost 100% or 1 unit. This case here, the ratio of the tooth to slot width is about 1 to 9. Tooth small, slot large, to the very large slot. The edge field change has a large effect on the tooth and nil effect on the slot. So here, this behaves almost like if it was a bar magnet moving with a conductor together with a conductor. So we have flux linkage occurring as well as flux cutting, and the effect is 0. And here, because we have a large slot, the effect is also 0. So in a circular multiple slot and teeth, the duty cycle ratio also determines the induction ratio. It applies only for cases where theta equals position angle. Okay, so again, there's the motion. Case of a large tooth and a small slot, the induction is the same on both, 1 unit and 1 unit. Case of a large slot and a small tooth, no induction on both. For the conductor on the tooth, it is like a bar magnet moving together with the conductor. From the perspective of the conductors on the teeth, and the field changes on the slot edges has no effect on the conductors on the teeth since the pair cancels. So looking from here, this is a pair, this is a pair, they have no effect. Multiple slots in teeth, voltage induction in the teeth and slot is 0.5 units in the same direction, cannot be used for return path. This is the case where we have the slot width equals the tooth width. So the induction is 50%. So you could say from a slot perspective, say we're looking from a slot perspective, it sees canceling pairs and therefore no induction in the slot. It can be used for the current return for the current path return for the conductor on the tooth. So from perspective of the slot, we see pairs and they cancel. From a tooth perspective, it sees canceling pairs and therefore no edge effect on the tooth, and only flux cutting induction occurs the same way as if no slots exist. But that's not true. The above says not true. If it were, we would have a way for the slots to shield and free energy device power. The slots in teeth are not in a straight, they're not in a straight line. And as previous case, the other edges do not cancel and have some effect. In other words, these two are not perfectly, there's a different angle from here to affect, say, a conductor here. This is a different angle and different position. So there's some effect. And it turns out if the duty cycle or if it's 50-50, the width, slot width, and the tooth widths are the same in this 50%. Suppose someone argues that the slots don't have any effect on other slots and that the voltage induced on the slot is not 50% but 100%, 1 unit. Then a free energy device is possible by applying the B field from below, from here, from down here, at the FR point, after the radius, to the R point, which is the top. The device is divided with slots with equal to the tooth width. At R, the B field is at the same value as at the RF, because half of it half of the area is taken up by the slots, which the B field doesn't go through. The inductions at Fr is half of the induction at R. The rotation at Fr is at half of the speed at R. The net induction equals induction at R times minus the induction at Fr, which is assuming it's 1 unit up here and half a unit here, so it gives you half a unit. But it's not true because it's not 1 unit up here, it's half a unit. The slot edges and angle also affects the induction. The edge angle is the same as position angle. Position angle is, this is the angle around the circle. So as the same edge as the same angle as the position angle. This is called the position angle. This is parallel edges, so straight. It's not the same as the position angle. Also has an effect. In reality, the core is circular. The position, the slot edges, and the edge angles affects the conductor and the other slots. In a straight case, yeah, you can say that the pairs cancel and has no effect on other slots or on the tooth. But in reality, it's circular. So the edge field changes on the side slot has an effect on the conductor and the top slot. For detailed analysis of the slot effects on other slots, see the video on slot shielding analysis. The next slide shows the summary from the analysis. So here's the summary. So that's what we chose. We chose to do with parallel edge slots on the left hand side, and the rotation is to the right. And from the analysis, it gives 1.5 is the effect. Here is 0.98. At position 2 is minus 0.56. Position 3 is plus 0.83. Position 4 is plus 0.2. Number 2, which is this one, has a negative effect on the conductor. Number 3 has a positive effect, but because it's more directly underneath and horizontal, it will have a more effect than number 2. The net effect on number 2 and number 3 together is positive. Hence why the total is over 1. The net effect is 0.83 minus 0.56, just for those two, comes to a net positive effect of almost 0.3. And the bottom one it's in the same direction as number 1. And also almost 0.2 positive effect. Apply the left-hand grip rule on the red vectors to determine the direction of induction on the conductor. So here we have anti-parallel edges slot on the right-hand side. So the effect, this again doing analysis if the B is going upwards, and the effect would be minus 0.5, but because in reality the B field is coming down, it would be also 0.5 in the same direction as with the parallel slots. The calculation was done as if the B field is outward, B field is reverse, positive effect into the page, negative effect out of the page. The total is minus 0.5. So basically what we have is, if we have a vertical vector, we have maximum induction when it's next to it. But as you go down below it, you have minimum effect with a vertical component. If you have the horizontal component, here has zero in effect on the conductor, but when it's directly underneath has maximum effect. So again, this is a summary showing different slot widths to tooth widths ratios. So slot voltage induced, so slot voltage induced is TW, the tooth width, over the tooth width plus the slot width times 1. So here is the case where a large slot width and a small tooth width. So slot width is 5:1, so the induction on the slot is 0.17, the induction on the tooth is 0.17. When the ratio is 2:1, the induction on the slot width is 0.33, the induction on the tooth is 0.33, both in the same direction. All of these cases, they're all both in the same direction. When the slot width is 1 to 2, now we have more on the tooth and less on the slot. So the induction on the slot is 0.67, the induction on the tooth is 0.67. So when you have almost like 5 slot width to tooth width 1 to 5, you got almost 0.83, and the tooth is 0.83. So when you have a small slot compared to the tooth width, this is approximating almost like a full it's almost like a full induction in one unit. When you have a very small tooth compared to the slot, this is almost like a bar magnet moving together with the inductor. And this is the case where the slot width equals the tooth width 1 to 1. The induction is 50% on both on the tooth and on the slot. When for a parallel slot, this is the case for 4, the induction is 1.5. For anti-parallel, the induction is 0.5 if the B field is outward, but if the B field is inward, then it'll be plus 0.5 and it'll be out of the page. So now we have the information to be able to design a high voltage homopolar generator final design. So summary: 4 slots parallel, 1.5 is the induction, the B field is upwards, the motion is to the right. So 4 teeth anti-parallel is minus 0.5, which gives you 1.5. So if you look at the teeth, it's still the same as in a slot, because when the slots is parallel, the teeth will be anti-parallel, and the result will be 1.5, the same as 1.5. So 1 unit due to flux cutting out of the page, and 0.5 units due to flux leaking, red arrows, also out of the page. So the sum becomes 1.5. So 4 slots anti-parallel. So now this is a different case where the induction is minus 0.5, which is into the page, and then the teeth will be 4 teeth will be parallel. The induction is 1.5, but the net effect will be minus 0.5. So both will be 0.5 and minus 0.5 and 0.5 to the interpage. 1 unit due to flux cutting out of the page. 1.5 unit due to flux linking, black arrows, into the page. Note flux link induction is in opposite polarity to flux cutting. The magnitude in direction of slot equals to the magnitude in direction of tooth in each case. However, the parallel slot magnitude is 1.5, while the anti-parallel slot magnitude is minus 0.5. Negative sign indicates that the direction is reversed. This allows us to construct a device as shown on the next page. So this is the approach we take. We're going to use a single coil, and we're going to have the B field go from the inner core to the outer core across and back down on the, so it goes up on the left side, down on the right hand side. Parallel slots on the left side, the induction is 1.5 units. Anti-parallel slots on the right hand side, the induction is minus 0.5 yield. But the B field is in the opposite direction on the right hand side. That makes the current induction the same direction as in the left hand side. This is the design approach chosen. Single B field coil in the middle and parallel slots on the left hand side, anti-parallel slots on the right hand side. We don't use the teeth because that way we'll eliminate the air gaps. So here's showing what the previous cases. So when the flux is going up, this is the induction okay, and when the flux coming down, this is the induction on the coil. Notice they face each other, so you cannot connect from this side to that side. And also, if you try to look like that here, the flux cutting, it will be in the opposite, will induce a voltage in the opposite direction to the voltage induced on the flux cutting area. Rotating stator induction coil and rotor together. Stator called outer core, rotor called inner core, conductor where the voltage is induced called induction coil, B field coil that produces the B field. Using multiple slots and teeth with slot to teeth ratio equals 1:1, slot edge, stator equals position angle. Induction is 0.5 on the teeth and 0.5 in the slot. Cannot loop the wires. The induced voltage on the vertical portion of the loop in the middle. In other words, the induced voltage here is opposite to the induced voltage here, and they cancel, so you cannot apply. Total induction in 1 second loop is 0. Same condition as above, but we use only the slots, no wires on the teeth. So this is to eliminate air gaps, but still we still face it with the same problem. So what we do is same condition as above. We use only the slots. The slot edge angles on the left side is changed to parallel, so we use parallel slot angles here. We use anti-parallel slot edges here, and the induction is 1.5. The induction is plus 0.5 because the field is downwards. And now we can connect the conductors in series, and we have a full path. The slot edge angles on the left side is changed to parallel, and the slot edge angles on the left is changed to anti-parallel. The horizontal induction on the left side is 1.5, and on the right hand side would have been 0.5, but the field is in the opposite direction, which makes it plus 0.5, which allows to be connected in series. Total induction in one segment is 2 units, 1.5 from the left, 0.5 from the right. Use only the slots. It eliminates the need for air gaps through the teeth. No conductor placed on the teeth. Return path on top of the outer core. So we'll place the return path on the top. So the slot edge angles parallel, left side. Slot edges angles anti-parallel on the right side. 0.5 unit induction, 1.5 unit induction on the left side. It is 0.5 instead of minus 0.5 because the B field is in the opposite direction from the left side. It is 0.5 with respect to B field down, but it is positive with respect to B field up. So rotation is clockwise, so it's clockwise from both sides. On both sides, the field produced on the external core, not shown, is counterclockwise, circular, and is orthogonal to the B field, black arrows, radio. Cannot operate as a motor. Anyway, suppose they are not, and produces a field as shown in the red using the right hand grip rule. The left side produces a counterforce clockwise, and the right side produces a counterforce clockwise, and they cancel. So we have two ways that works against not be able to operate as a motor. If the field produced is circular and it's orthogonal, so there is no force, or because on the left hand side the B field is vertical outwards, on the right hand side the field is downwards, and the current is in the same direction, so this creates a counterforce to the left. This creates a counterforce to the right. Again, the torque cancels. So there's no way you can operate as a generator, as a motor. View from the left hand, parallel slots. So this is the parallel slots. The B field comes in, up, and goes back in through the outer core and produces a rotating field. View from the right hand, anti-parallel slot rotation. Black is the B field path. Blue is the magnetic field produced by the induction coil. Brown. The induction coils are the brown. Red is the induction coil current direction. The coil loops up to the top of the outer core. Requires cuts in the outer core to prevent saturation from induction coil magnetic field blue. Kind of torque or the Moore effect cannot occur because the B field black and the induction coil magnetic field blue are orthogonal. This device can only operate as a generator. The magnetic field produced by the generator circular in the outer core is orthogonal to the coil B field radial. Air gaps were placed in the outer core to prevent the induction coil magnetic field from saturating the outer core. Even if there was a counter torque produced by this magnetic field, the torque produced by the parallel slots would be in the opposite direction to the torque produced by the anti-parallel slots. The current on both types of slots is in the same direction, but the B field direction are in opposite direction. Thus, any torque developed will be cancelled. So the calculation, B field coil calculations. So the mean path length of the B field, the black loop wire, this is the magnetic path length, is 2 times 125 plus 50 plus 50. So this is 125, this is 50, it's 450 millimeters or 0.5 meters. For 1000 ACLBH curve for 1.2 at B field at 1.2 Tesla, H equals 400 ampere turns per meter. The required ampere turn is 400 ampere turns per meter times the magnetic path, which is 180 ampere turns. The B field area is, this is the B field, is 5 millimeters by 50 millimeters long, and it's 250 millimeters square. Choose 1 millimeter diameter wire carrying 1 amp. We can at least fit 200 turns or loops in this area, giving it 200 ampere turns. So we got capacity for 200 ampere turns here. Total length of the B field coil is 2 pi 1.25 millimeters. So in other words, the radius up to here is 125 millimeters, and it's 200 turns, so it's 157 meters or 0.157 kilometers. The resistance of the wire is 20 ohms per kilometer. The resistance of the field coil is 20 ohms times 1.57, 3.14 ohms. Power consumption is I squared R is about 3.14 watts. Runner off to 5 watts. So 5 watts, no more than 5 watts for the power dissipation of the B field coil under worst case conditions. Now this for the induction coil, it's 125 millimeters up to the bottom of the B field coil. It's 131 millimeters to the bottom of the induction coil, and 147 to the top, which this width is about 16 millimeters. The midpoint is about 139 millimeters. So generator induction foil calculations. Voltage is equal to BWLR, normalized to 1.888 volts per turn. That's for when B is at 1 Tesla, W is at 1800 RPM, L is 100 millimeters, R equals 100 millimeters. So the B average, we use 1 Tesla, so we're going to go with 1 Tesla. So the factor for B is 1. We're going to use 1800 RPM, the factor is 1. We're going to use L at 125 millimeters, so the factor is 1.25 because L is 100 millimeters, but we're going to use 125 millimeters. The R mean is 139 millimeters, so the factor is 1.39 because it's 100 millimeters here. Also, the parallel slots is 1.5 times, and the anti-parallel is 0.5 times. The total factor due to the slot edges is 2. So when we adjust, it's 1 times 1 times 1.25 times 1.39 times time. That comes up to 6.5 volts per turn or per segment or loop. The B field only goes through one disc area, which is half of the area as compared to the cylinder surface. Then L should be R over 2. But because half of the cylinder surface area is taken up with slots where B field doesn't go through the slots, therefore L equals R to keep the same B at around 1 Tesla. But the radius of the slot is at 100 139 millimeter versus the 125 for the B field core. We can adjust the B field to about 1.2 Tesla to give about 1 Tesla at the top of the slots, where R max equals 147 millimeters. This is not a problem since there are no air gaps and the B field coil is small. See previous slide for calculation B field coil to give B equals 1.2 Tesla. That's why we chose for the B field to be 1.2 Tesla to give about 1 Tesla at the top of the teeth, on top of the slot. We're not using any more conductors on the teeth. So available slot area at 125 millimeter radius, the circumference is 2 pi r, which is 785 millimeters. There are 4 slots and 4 teeth, so we divide by 8. That gives us about 98 millimeters. So we choose 9 millimeters as the length available for the wire. The height of the slot is 16 millimeters. We choose the available height is 14 millimeters, the height available for the wiring. Therefore, we choose the area of the slot available for wiring is 14 times 9 is 11260 millimeters square. We choose 1200 wires, 1 millimeter diameter, 1 amp for each slot. So each slot is 1200 ampere turns. For 4 slots, it's 4 times 1200, which is 4800 ampere turns. From the previous slide, the calculated voltage induced per turn is 6.5 volts per turn. The total power delivered by the generator is 6.5 volts per turn times 4800 ampere turns. It comes up to 31.2 kilowatts, run it off to 30 kilowatts. So induction coil power consumption calculation. The length of each turn is 0.6 meter, calculated in the previous slide, and 1 millimeter diameter wire resistance is 20 ohms per kilometer. The total resistance of the induction coil is 4800 turns times 0.6 divided by 1000 meters per kilometer times 20 ohms equals to 57.6 ohms. The power consumption of the induction coil is 1 amp squared times 57.6 ohms comes to 57.6 watts. Run it off to 60 watts. This generator in the size of about a foot cube can supply 30 kilowatts and it consumes less than 65 watts. Size and volume. Outside diameter is 400 millimeters. Depth or length is 300 millimeters or 30 centimeters. The radius is 200 millimeters or 20 centimeters. The volume is pi r squared times the depth. 3.14 times 20 times 20 times 30 equals 37,680 cubic centimeters. In cubic feet, centimeters to feet multiplied by 30. So it's 2.5 centimeters times 12 inches per foot. Cubic centimeters to cubic foot is 30 times 30 times 30 times. So it's 37,600 divided by 27,000 equals 1.4 cubic foot. Weight calculations. The density of copper is 8.96 grams per centimeter cube. The density of 1008 steel is 7.872 grams per centimeter cube. Use an average, say, of 8.5. The weight is 8.5 times the volume, which comes up 320,280 grams, 320,280 grams, or 320 kilograms. So in summary, so this is the right side where the B field goes inwards through the teeth. This is parallel teeth and anti-parallel slots. The B field on the left side goes up to the outer core on anti-parallel teeth, and we have parallel edge slots. So the induction is 1.5 on the parallel slots, and induction is 0.5 on anti-parallel slots. And this is one side of the coil. So it will loop on the outside through the outer core. So this is the parallel edges, parallel slot edges. This is the anti-parallel slot edges. This is 90 degrees to this. Again, this is a cross section showing the induction coil here, and this is the B field coil. And there's 4 slots, and this will wrap a loop through the outside Again, this is another cut version showing where the B field coil goes. This is the parallel slots, anti-parallel slots here, and anti-parallel teeth, parallel teeth. So this is where the B field coil goes inside here, and the coil goes from the parallel slots through the anti-parallel slots and wraps on the above the outer core. So there's showing how you place the coil. This is just the envelope, showing the envelope. And then there's three ways of looping through the outer core. Either we place it on top, right above it, but I don't know if there's any effects from the slots edges affecting the coil on top of the outer core. So you can offset by placing above the teeth instead of directly above the slots. Or we can flatten it out. That almost takes the whole entire area, so 4 flatten it out. So this will make it more compact. So this device can only operate as a generator. The magnetic field produced by the generator, circular in the outer core, is orthogonal to the B field radial. Air gaps were placed in the outer core to prevent the induction coil magnetic field from saturating the outer core. Even if there was a current torque produced by this magnetic field, the torque produced by the parallel slots would be in opposite direction to the torque produced by the anti-parallel slots. The current on both types of slots is the same direction, but the B field direction are in the opposite direction. Thus, any torque to couple will be cancelled. So how come it saturates? Because this is the B field magnetic path, and if we don't place a cut here, it will saturate. So we need to place cuts. 5mm cut on the outer core in 4 places to prevent outer core from saturating. So there's one way of assembly. You can have assembled this way. This is the B field coil, and this is the. I don't show the connection from here to there, but I show in the end. There's another way. You could have the ring placed here and the B field come here, but I don't know how you hold this together. I think this is better to hold it together because this holds the whole assembly together. So parallel slots on the left hand side of the generator. So this is the parallel slots. This is the sleeve. We place a seal to hold everything together. Anti-parallel slots on the right hand side of the generator. And this is how it's looped from inner core to above the outer core. You need to observe the precautions when handling high voltage above 50 volts. Be knowledgeable about high voltage hazards. Here's some more design precautions. Slot insulation paper to insulate the copper coil from steel core to prevent an electrical short. Lacing of coils to prevent unwanted vibration that can cause fatigue and failure during operation. Magnetic wire insulation breakdown voltage. Like other wire, magnetic wire is classified by diameter, AGW number or SWG, or area square millimeters, temperature class, and insulation class. Breakdown voltage depends on the thickness of the covering, which can be of 3 types, grade 1, grade 2, or grade 3. Higher grades have thicker insulation and thus higher breakdown voltage. Breakdown voltage is 200 volts per micrometer. Example, 12 microns thickness of insulation. Insulation breakdown is thickness of insulation times the voltage breakdown, which is 12 microns times 205 comes to 2460 volts. Slip ring connector. Slip ring connector is an electromechanical component that provides the electrical connection between a rotary and stationary parts of the machine. It's also called the rotary electrical connector or rotary electrical interface. Through-bore slip rings is a hole in the center of the slip ring where the shaft is inserted into. It is normally installed by fixing the outer ring where the inner ring rotates. So this is the inner ring. this is the part that rotates. This rotates with the device, and the other part is stationary, and this is where it goes to the outside world. Now I list here two types. You can get it from Roricon or you can get from Montflon. This is only a suggestion. And here's I showed the specs for a series, the 1256. And the one I picked is one that has 16 contacts at 10 amps and 2 contacts at 5 amps. This is the 5 amp ones are used for the B field coil, and those 16 contacts are used for the induction coil. So the GT1256 P6010 is rated for 1800 RPM induction coil, 16 power contacts designated P at 10 amps, need to combine into pairs, 8 for supply side and 8 for return side. The maximum voltage is 440 volts DC, maximum power is 440 times 80, which is 44 kilowatts, or okay for the high voltage high power generator because it's rated for 30 kilowatts. The B field coil, 2 signal contacts S at 5 amps for B field. The B field only requires 1 amp, 1 contact for supply side and the other contact for the return side. Also, to mount the motor or the generator, you need a pillow block, or there's 2 examples of pillow block bearings. So you have a stand, and you have the bearings on either end, and you have the slip ring connector. Then you have the connections. The rotary part of the slip ring connects to the rotary part of the generator. The power contact on the slip ring has a maximum current rating of 10 amps and a maximum voltage of 440 volts. At 400 volts and a given number of power contacts, choose a series parallel combination of the induction coil wiring to achieve that meets the current rating, the voltage rating, and capable of delivering the generating maximum power. 8 pairs for induction coil, 1 S pair for B field coil. There are many ways of connecting the induction coil wiring to series parallel combination to fit a slip ring connector, depending on the number of contacts and the maximum current and voltage rating of each contact. Example, slip ring connector has 16 power contacts, each rated at 10 amps max, 2 signal contacts S, each rated at 5 amps max, all contacts rated for 440 volts maximum. Induction coil. The high voltage homopolar generator has 4 slots, each slot with 1200 wires, loop or turns. 8P contacts are used for the supply side and 8P contacts are used for the supply return. 8 pairs or 8 coils for the 16P contacts. 4 slots, each slot will have 2 coils per slot. 1200 wires in each slot, each coil will have 1200 wires for 2 coils or 600 wires per coil. Each wire carries 1 amp, and therefore for 10 amps it is 10 wires connected in parallel. With 10 wires in parallel, each coil will have 600 divided by 10, 60 turns. 60 turns of 10 wires in parallel. So we have 2 coils per slot, 8 coils total, each coil with 60 turns at 10 amps, 10 wires connected in parallel. The voltage induced per turn is 6.5 volts per turn. The output voltage for each coil is 6.5 volts times 60 turns, which is 390 volts, and 10 amps per coil. Maximum power output is 8 coils times 10 amps times 390 is 31.2 watts or 31.2 kilowatts. The high voltage homopolar generator is rated for 30 kilowatts, so it's a good fit. So we have on the anti-parallel slot side, there's an opening and for bringing in the S single wire pair to the B field coil in the middle of the generator, because that's the only way we have access to it. Each slot in the wiring is split into 2 coils, 1200 wires loops or turns in each slot. Each coil is 600 wires. Each coil configured for 60 turns of 10 wires connected in parallel, 390 volts at 10 amps. So capability, the green generator, high voltage homopolar generator. The size is 400 millimeters diameter by 300 millimeters long, or 16 inches diameter by 12 inches long. Volume is 1.4 cubic foot. The weight is 320 kilograms. The output is electrical energy is 30 kilowatts. The power input consumption is 0.1 kilowatt. Okay, the logo, the squares represent the 4 parallel slots on the left hand side. The triangles represent the 4 anti-parallel slots on the right side. And that is the end of the presentation.